See if you work. Okay, so any questions from homework?
None of the math or none? What this?
I have a question on 68.
Why?
Where we at?
68.
In where?
5.2. I found all the information they were talking about. I'm just not sure how to use it to graph.
Oh, yeah, good. I like this problem.
Philosophy? Yeah.
Who's your favorite philosopher? Favorite philosopher? Well, I'm thinking logic.
Because, I mean, the derivative is just equal to that equation.
Yes. Oh. I want to say Aristotle, but...
I can go to. Yeah? Okay, yeah. Well, yeah.
I really want... Yeah, it's okay.
Oh, yeah.
Which
He asked me what my favorite philosopher
68.
So we're going to look at 67.
Well, I mean, that works. It's just, I got the information, I just don't know how to use it to graph the frickin' thing. At least I think I got the information.
So I have like a 30-minute break and I usually eat.
All right, guys, so there's a problem. The problem you actually have to do is 68.
Yeah.
So to be very helpful, I'm going to look at 67.
Omega. Yeah.
All right. I like this problem a lot.
What problem?
67?
We're going to look at 67.
5.3.
5.3.
Homework is 60.
5.3. All right. So g of x is defined to be the integral of that function from 0 to x. So what's a better way? So guys, what's a more English way to state what g of x does?
The area of G of X.
G of x, area under f from 0 to x. I like it. So g of 5 would mean what?
The area under a curve.
Yeah. How much area have accumulated from 0 up to 5? I like it. You with me so far? So that's what intervals mean, is the area.
Okay.
So what values of x did the local max and min values of g occur? Right? So there's a couple different ways to look at this. So one way you could look at it is I'm accumulating area under f. So for example, up till here, and then a little bit past here, what are true about my values of g? They're going to be positive. I like it. Somewhere, now does everybody see, somewhere, maybe about right here or so, right? I hit what? G of this would be roughly 0. Because you see that this area and this area would cancel. Because this area is negative. Negative because it's below. Man, that was a sentence with a lot of blanks. So, but if I get all the way to here, what do you guys think? Will G be positive or negative by this point? Positive. Because it's more positive area than negative. In fact, that looks like it's bigger than that, right? So that by itself would cancel it out, and then you have some extra stuff. So one way to look at it is try to figure out, okay, where would I have accumulated the most area? At what point will I have accumulated the most area? So it looks like these two basically cancel each other out, right? Which one looks bigger? This one's got a negative 2 point something. That one goes to
3.
a little bit. Yeah, it goes to almost like 2.5. So okay, I agree with you. That's a little bit bigger than that. All right. So obviously, I haven't gotten very much area here, but then it becomes really negative. And then by the end of this, do I have more or less area than I would at the end of this? More. I like it. Because that's a little more than that, plus that, right? You guys understand what's happening here?
Yes.
So it's just a change in how I look at things. Right? Now, did you try to do it a different way? And again, my point here is I'm trying to figure out by what point will I have accumulated the most area while continuing in this fashion. What does it seem like that might happen?
I just did it.
Probably here, yeah. Because by the end of this, I've accumulated more area than anywhere up to that point. Then I lose some, but by the end of this, I gain more than I lost. So it seems like the maximum would have happened here.
For your absolute?
Yeah. Well, yeah. Because that occurs at an endpoint. It's got to be an absolute. I like it. Right? So at what values do the local maximum values? Okay, so now let's talk about local maximums.
Yeah.
I like it. So obviously, hopefully, let's find out. So I'm accumulating area until here, and then the minute I move a little bit past here, I'm losing. So that's going to be a max, right? So what's the other way to look at this for the local maximum? Where's the min going to happen?
At 3.
Yeah. So yes, sir.
At every inflection point, there's going to be a.
So now watch. This might be the way you looked at it. If I take the derivative of g, what do I get?
F of t.
Yes, f of x.
Yeah.
Right? So f of x is the derivative of g. So at what points do local maxes and mins possibly occur?
That's why I do.
Where the derivative is 0. So these are where g prime is 0 because g prime is f. I like it. All right, cool. But I wanted to start with the weirder way to look at it, just to really show you can look at it directly as areas. It's an accumulation of area. I like it. So part A is not too bad. Part B, where does G attain its absolute? So we did part B already. Part C, on what intervals is G concave down? I like that.
So for this one, I just kind of guessed what F double prime would look like. I'm not really sure.
Well, if you're looking for the actual maxes and mins on there, so local maximum.
All right. So F is G prime.
Yes.
So F prime would be G double prime. And inflection points might occur where the second derivative is.
Oh, it's like 0. It doesn't exist.
So where the second derivative is 0 would be where the slope of the first derivative is flat. Yeah. Right? So I think that's what you're saying. I like it. Okay, so all right. You guys kind of see where to go from there.
Yeah.
Try not to. All right. Sketch the graph of G. Well, then you just kind of estimate. You take points. Like I would take this point, and I'd say how much area have I accumulated so far? And just take a rough guess. Obviously, like this would be an area of 1, so maybe that's a third of it, right? So I would say G of 1 is 1/3. Does that kind of make sense? You could do that. You could also use some of what you discovered before that. They're helping you out with the, because you know where the local maxes and mins should occur and all that kind of stuff.
Yeah, that's what I wrote down was the local maximum, but I was like, where do I put these?
So the next thing you can do, one more thing, in addition to what they ask you to do, you can actually just, at 1, it looks to be about a third, an area of a third that I've picked up so far. Does that make sense? So at 2, I'm negative something, so maybe that's a third, and then maybe that's maybe a negative 1/3, right? And this is an estimate, so who cares if you can't be perfectly right? But I don't know if you guys are with me. I can pick out specific points and then estimate how much area I've picked up to that point, because that's what G does. G of 5 would be the amount of area I picked up by this point. So can you guesstimate how much area you've picked up to that point? Sure you can. Doesn't have to be perfect. But you also marry that with the stuff you figured out already, where the maxes and mins happen, you make sure those happen in the right places. Yes?
So because f of x is a derivative of g of x, then g of x is the integral of f of x, and that's why you
Well, that's how they define it, yeah. G of x is the integral, therefore f must be the derivative. I like it. Okay, alright. Just to give you the right way to look at that kind of problem. That's why I like that problem. You can use very analytical, take derivative methods, but you can also just realize I can estimate the area. That's what it means. It's the amount of area I've picked up so far. That's what the G function means. Okay? Anything else from homework? Yes, sir.
Could we go over
No.
55. 5.3, 55.
All right, so let's see. They give you. Oh, okay. So I was about to do this the other day. 5.3, right?
5.3.
Yeah. So we did problems like this, and of course, really quickly, if I had, it actually doesn't matter what this is, but if I had, it doesn't matter. If I had this, what, Jeff? I don't know, Jeff. Leave me alone, man. ln of good times 3 because the derivative of the inside. I like it. Is that cool? That's the f top 1.
So that would just be F.
Yeah. Well, so if this is G,
Or just T, sorry.
if this is G, then yeah, this would like be this would be like F, right? That's the same thing what we just saw. G prime equals F. So G prime equals F of X. But again, I'm taking a derivative, so the derivative rules still must hold. So that's not just X, it better get its term, that's chainable. So the problem they give you here has got X's on holy freaking shit. Right? What the freak? Now I want you to pay attention, you got to really realize that no matter what they put here, this is not the hard part. That is the easy part. I don't care how ugly they make this. That's the easy part because I just throw shit in there. This is where they can mess us up. So those are not difficult functions, but I'm supposed to have constant to something, right? So they tell you. Actually, I wish they wouldn't have said this. They tell you what to do.
Can you do properties?
Stupid thing. Then you take the derivative. Now, what do you have to do with this, though? Is that
Negative.
So the derivative of this would be f of 2x times 2, and this would be f of 3x times 3. Negative, because you got to do a negative to flip this. Right? Not a big deal. Because they told you this. This is the key. Right? Because you have a rule for when there's x on one side. You have a rule for that. I don't have a rule for this. Just like I have a rule for this, and I have a rule for this, but I didn't have a rule for that, so we had to come up with a process, right? That's when I took the natural log. Same exact thing. I don't have a rule for x's on both sides. Here's the process that I use to make it look like the rule. Okay. And the crowd goes apathetic.
Did you go on top, you just multiply by negative and that's it?
Oh, yeah. So this part here is in the wrong form, right?
Yeah.
What do they use? U. So that's just negative. Get out of 2. So do that first, and then attack it with derivatives. Yeah.
For whatever reason, I thought it said solve.
Oh, hell no. That's a little tiny bit beyond us at the moment. Yeah. Actually, you could do that.
Yeah, I was thinking maybe you'd take
You
them
can use
apart.
it's like a derivative of a trig function, an arc trig function that gets you there. But no, you don't have to do that here. Don't worry about it. You right? Good? Yes? All right. So anything else from homework? Yeah.
So we do from 5.2.
Yeah?
28.
We did that one, didn't we? Yeah, we did that one. Now, of course, you're like, that's easy, but 5.2, we can't use the shortcuts. Yeah, you have to do the whole delta x and all that kind of stuff. Yeah. And it's just one of those problems, you just gotta do the steps. You gotta brute force that bad boy. Not everything in life can be looking nice. Alright, anything else from homework? Okay.
So, let me ask you this.
Hey guys, let me ask you a question. Since we actually have classes actually happening right now. So, what do you guys think about this here? All right, let me start off nice.
Plus C.
It's crazy, right? So far, so good. And what about you? Ready?
Cosine
I don't know if you're ready. You're not ready. You're not ready. You're not ready. Don't overthink it. Don't overthink it. 2 sine x.
Plus C.
So we never actually looked at this, and I almost did this a couple times, and I decided not to. But you ready? Watch. So back in the day, if I did this, back in the day, that would be what? 3. Because we're doing the derivative with respect to x. So any x I see, I do the derivative of it, right? So watch. If I did d by d, there's 3. D by d 3x of 3x, that would be 1.
Yeah.
And look at it, d3x divided by d3x is 1, isn't it? Right? So this doesn't have to be a single variable, it could be an expression itself. Now with derivatives that doesn't happen very often, but with integrals it actually happens a lot. In fact, it becomes a key component of some of the processes we use for integrating. So this would be kind of weird if we're just talking about differentiating, because this doesn't really happen a lot. So if I had d by d sine x of sine x squared,
It'll be 1/3 sine x to q.
d by d sine x.
Sine x cubed.
It'll be
Sine x 2 sine x. Done.
What?
Oh, because you're taking the derivative of just sine.
Because what's d by dx of x squared? 2x. So what's d by dy of y squared? 2y. So what's d by d sine x? So sine x squared. 2 sine x. Bam! How much? Yes.
Are you just taking the derivative of sine x squared?
Yes, with respect to sine x. So now what? You ready? One thing we do to make it easier to look at is I replace sine, I replace it with u. So what's d by du of u squared? 2u. Isn't that exactly what the damn thing says anyway? You just put a sign back in for u. So this extends the idea beyond this being a variable. It could actually be a variable expression, right? So u very often is what we use most of the time. Some of you guys know where this is headed eventually. But u represents a function of x or t or whatever your real variable is. You guys kind of with me so far? All right, so what does this have to do with the damn thing? I don't know anymore. I had a thought. Let's see. So what's this here then?
With respect to what?
It's just
Oh, wait.
What's understood to be here?
1.
What?
0.
So tangent of
What's the integral?
Tangent of x
Yeah, it's tangent right x.
plus c. Sorry. Oh.
Because what's the integral of dx?
1. Oh, x.
X plus c, because there's an understood 1 here, right? Now, but look, the reason I like this, dx is the differential of x. So if I integrate the differential of x, I get freaking x. If I integrate the differential of tangent squared x, I get tangent squared x. I like that. Can I do it now? All right, maybe. So, what does that have to do with anything? Oh. This section 5.4, it makes a big deal out of this. Let me think. I want to see what. Let me do this first off of this, and then we'll do a visual of what this means. This is almost too silly. Yeah, and watch this. You ready? No. Isn't F prime is this, isn't it?
Yeah.
So I just replaced this with what it is. What's the integral dfx?
C.
I was waiting for my C. So that kind of just cuts through the shit that we went through, kind of. It's hiding a lot of stuff when you do this, but we went through the whole proof that the integral of this is actually an antiderivative of this, which is really what this kind of directly gets to. I don't know if you guys understand what's happening. Of course, this whole thing, it uses what we proved, so it's not really its own proof, but it's a nice, quick visual of how things work together, and of course why things like this work, or using that to prove this. So one thing this thing talks about is if I have a velocity, if I'm going at constant velocity, if I graph this, I'm going at constant velocity. So if this is the velocity function, I'm going at constant velocity, what's it going to look like? Straight line. So let's say I'm going at 10 mile an hour, right? Because I picked the wrong time to go on the road here in San Diego. 10 mile an hour sometimes is like, oh yeah! Sorry. You understand, if you drive, you know what I mean. So after 5 hours, how far have I gone? 50 miles. So now watch. Isn't that's the what of this function? That is actually the area, which is the integral. So the integral of the velocity. Well, what's the velocity? It's the derivative of the position. So anytime I integrate a rate of change, it tells me how much the thing actually changed by. So my position changed by the integral of the velocity with respect to time over this region, right? And then really it's just doing this again, right? I don't know if you guys see what's happening. So if you have a rate of change and you integrate it, you get how much the thing it's measuring changed by. So this is a rate of change of position. When I integrate it, I get how much my position changed by. Right? I like it. So if I had a constant acceleration, what would that look like for velocity? If I had a constant acceleration,
And we're representing the velocity, it would be
constant acceleration would be constant acceleration.
It's just positive.
Velocity, exactly. So you're doing a curve. I don't like that.
You like that?
No, I don't. Constant acceleration. Acceleration is so it's the slope of velocity, right? So if I have a constant acceleration, I better have a straight line velocity. Let me let you absorb that for a minute. Absorption.
if it was a distance graph, it would be like
Yes, if it was the position, it would have to be curved. I like it, but that's not what I said. So if I'm going this, let's say, so this is where, let's see. So I start off going nothing, and then I build up to 10 mile an hour. Well, after 5 hours, how far have I gone? That normally would be a difficult question to answer if you think about it. A constant velocity is easy to answer. If I'm going 10 mile an hour for 5 hours, and I've gone 50 miles an hour. I'm 50 miles. But now my velocity is constantly changing, but now we realize that question is easy. All I have to do is find in this case, the area, because I got the triangle staring me in the face. But no matter what it is, I can make it look like anything. Curve, whatever. I find the area to see, so whatever the velocity is, it could be changing. I could have jerk in there, right? My old car, right? I think I can, right? I just get the function that represents that, integrate it, that tells me how far I've gone. Thank God. So before this, you could only have constant velocity and really figure out how far you've gone. You need calculus to help you when you have the fundamental piece itself is changing, right? So if it's not changing, it's easy. Distance equals rate times time, dirt. But distance equals rate times time does not work if my velocity itself is changing. Because what does this formula depend on? The fact that r is a number. And here, r, my rate of movement, is constantly changing, right? So I want you to realize this. So, for example, if I'm modeling a rocket ship heading off into the atmosphere, I can't use anything, because what's happening as the rocket ship is going up higher, how is it actually moving? It's burning fuel, and when it burns fuel, its mass decreases. Oh, shit. So, to really be able to accurately describe its motion, I need calculus, because a fundamental part of it is changing over time. I can't do something easy like this. I didn't need calculus for this, did I? I just needed dirt. D equals RT. But the minute that something is changing over time, I need calculus.
Don't you just try to find like average velocity and then you go from there?
To find average velocity, if my velocity function looked like this, I'm glad you said that, because very soon, well, not too soon, but we could do it right now, actually. You use integration to find the average velocity in any case. Because how do you find average of anything?
You add everything up.
You add them up, which is the area. You add them up, and you divide by how many there are. So if I integrated the velocity from 0 to 5, and then divided by 5, that would give me the average velocity. And that's the same damn thing. We add them up, divided by how many there are. The average formula doesn't change for calculus. It's kind of awesome. All right, that's coming. That's still in our future, but that's a pretty simple idea. Cool. I know. All right. So how are we doing so far? So part of this section 5.4 is it's called the Net Change Theorem, which is just really silly. It just means if I want to know the net change of position, I integrate the velocity. I integrate the rate of change of that thing. You guys kind of with me still. A little tiny bit. All right. We're with you a little tiny bit, Jeff. Okay. I don't know why I made you sound like that. I'm sorry. It's all right, Jeff. Let me ask you this. I kind of did this really quickly the other day, but I want to make a big point of this right now. Why is this? Well, what is this? So I glossed it over for two reasons. If I try to use the formula, what happens? What's the formula?
X to the n minus 1. Oh yeah, that's 1 n plus 1. Plus c.
So if I try to apply that here, this is x to the negative 1. You already wrote it, Jeff. There it is, Jeff. Yeah. I get x to the 0 divided by...
X.
No,
1 over infinity.
So this rule only works if n is not negative 1. We know what this integral is, and this is the second thing I kind of glossed over a little bit. So the first thing is, this rule that we learned, the easiest rule there is, doesn't work in one case. Because otherwise you get, it can't be, right?
For all negative exponents?
No. Only negative 1. If n was negative 2, this would be x to the negative 1 divided by negative 1. That's fine. So it's only if n's negative 1 that will get an infinite or undefined result. Right?
Don't we have that?
No limit. So
Don't we have that similar rule which we have in the product rule though?
no, we don't. That's the beautiful thing, because the product rule has a dead end. Right? Because what's the derivative of x? So what's the derivative of this in general? It's n times x to the n minus 1, right? What happened? He's no longer looking this direction.
I figured it out.
All right, I got you. So the only place there might be a problem is there, and it's not a problem because its derivative would be 0 times x to the negative 1. It's 0. And what is x to the 0? It is 1. So the derivative of the constant we already know is 0. So that rule is self-sufficient. It just has a dead end. And I pointed out to you guys, I don't know if you remember, that natural log of x is like the bridge between positive roots and the negative roots in a way. So what is this then? This is the
absolute value.
beautiful. Why the absolute value of x?
So you can take the negative values.
Because 1 over x works for every x except 0. So your answer better work for every x except 0. So that I have to have absolute values there, of course. I like it. That was creepy. I like it. That was creepy. Alright, good. Gotta work on my level of creepiness. And some of you guys are like, no, Jeff, it's alright. You're right. Alright. So that was that. What else have we got here? I had somewhere else I wanted to go. Alright, we might as well jump into that. I like it. Jump. Everybody's like, jump. Oh, so I just want to make sure you guys are looking at some of these products. Just like when we first learned derivatives before, we knew there was a product rule, we had to FOIL and stuff, right? So there is no product rule for integration. There is an answer to product rule for integration, which is a process, right? Which we actually won't even learn this semester. It happens next in 280 if you're so lucky to take that. So if I have something like this, do not integrate the top and the bottom separately. Who the hell, why would you expect that to work? I can't differentiate the bottom and the top separately. And integration is always at least as hard as the derivative would be. Most of the time that is a strict greater than. Meaning the level of difficulty integration is almost always greater than the level of difficulty derivative. So if I'm not allowed to do that simple, if I can't make it that simple, I gotta use quotient rule. When I integrate, oh shit. But what saves me here is I can break it up, right? There's only one thing on the bottom, so this would be integral of x to the 2/3 minus
X to the 1/6.
x to the 1/6. Kick ass. Right? 1/2 minus 1/3. Cool. And now that I can attack with the rule twice over. What would it be now?
3/2 x to the
No.
5/3.
oh.
Yeah, so 2 plus 3 is 5 over 3. You find that first, because that's n plus 1, you divide by n plus 1, right? So find it first, and then you multiply by the reciprocal.
So 3/3.
Find the power first.
7, 6.
1 plus 6 is 7, 7, 6, and then you multiply by the reciprocal.
Plus C.
Cool. Yeah.
So if we take the integral of that expression, would it be xc?
Oh, okay. So, alright, let's say that, so they tell us that this is f double prime.
Okay.
So what did we just discover?
F prime.
F prime. So how do I find f?
Doing it again.
So you do it again.
Yeah, I integrate it again. I like it.
And you get C.
Keep going. Here we go. You ready?
So, yeah.
Let's see.
Yeah. Is it like
8.
8?
So 3/5 times
X to 8.
x to the 5 plus 3 is
8.
over 3. So what do you put in front?
3/8.
3/8. Do you see how to attack that? Find the power first, because then that's what you divide by. Because the fraction you multiply by the reciprocal. Let that be simple. You just got to get used to it. Minus 6/7 times x to the 13/6. So you put in front 6/13. Like you said, this will be cx plus
D.
Wait, why
We could really have we had 2 C's.
because you can't assume that this number and that number will be the same. Which is, if you write the same symbol, you're assuming it's the same.
Could you not just put C?
You could put C2, right?
X plus D.
You can't replace a variable expression with a constant. This expression depends on x. So you can't take this whole expression and replace it with a constant. Do you see what I'm saying? If I integrate it again, this would be 1/2 cx squared plus dx plus e. That's crazy. Plus e.
Go down the alphabet.
What if you run
Go down the alphabet. Huh? Then you start using Russian letters. Greek letters. Right? Thankfully I've never run out of letters. Or what you actually do, if you're going to take like diff and q, where you end up with like a lot of constants sometimes, you don't use C and D, you use C1 and C2, and then you can have an infinite number of those, right? C 48,500,000. Day 8,000.
If you were to integrate again, would you keep the for the first term?
I'm sorry. So of course, I mean this part you have to simplify. My bad. 36 over whatever the hell. Blah, 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 right? And if I integrate again, I would attack it the same way. I would take that by itself, figure out what that is, and then simplify. I always move the constant over for a second, and then I slam them together next.
So would you get cx squared plus cx, right?
You would get 1/2 c1x squared plus c2x plus c3 if you integrated one more time. Is that cool?
Yes.
Okay.
And you said we can only do that when it's only one variable at the bottom. I'm talking about the very top.
Yeah, exactly. So right now we can't. Well, how would you do this? Exactly. I heard that. That's perfect.
Well, first off, factor the top.
Can you factor the top? If you can, you're better than me. So I'm ready to learn. The end of Kung Fu Hustle in my head.
Would you try to do long division?
Huh?
Would you try to
Yeah, long division. Or synthetic is even better. Yeah, I'm teaching my Math 90 class long division, so now I'm like stuck on this. But sweet dear Lord, tell me you guys know synthetic division.
Yes.
If you don't, my God. What do I put?
-0.
But I know
0.
Oh, yeah, -4.
Why is there a 0 there? Because there's no. So 1 times 1 is 1, plus 0 is 1, times 1 is 1, plus -4 is -3, times 1 is -3, -1. So I get integral, what's that become now?
X cubed, or x squared, plus x minus 3, remainder of 1.
Good, so what do you get? What do you get?
Oh, x cubed over 3 divided by 3 plus x squared over 2 minus 3x minus, minus c.
What's this? What's this? ln of x, so what's that?
Plus c.
Let me stop there for a second.
It's beautiful.
Yeah, this is my dissertation defense. It's a lot of people to do that. Oh my God. Okay. So real quick, on the notes of this. Today is Tuesday, Thursday. It's a Tuesday, Thursday.
It's Thursday. It starts with a T, ends with a Y.
What's that?
ln of 4x.
Ln absolute value of x minus 3 plus c.
Plus,
Oh, times 4x.
No. Divided by 4.
Divided by 4. Why divided by 4? Man, you guys are as loopy as I. That's different. So this is very similar to this, of course, right? I mean, this would be the same kind of thing. What would that be?
e to the 4x minus 3 over 4 plus c.
Because you put that over 4 to be the booby trap for the 4 that wants to come out. It kills it, right? It's like, I am dead. No. So the 4, if I took this derivative, there would be a 4 because of chain rule.
Yes.
That 4 kills it because I don't want a 4. It's not there.
Nobody
If there was a 4 there, then I wouldn't need that, would I?
No, you would not.
It's like that would just kind of get reabsorbed back up there, right? Exactly. I'm glad you guys make the sound. Yes.
Just a quick question about going back to C. If you integrate twice, 3 times, and you get the x squared, would you do it over 2 still?
Of course. C is just any number, and when you integrate, the constants don't mean shit. What matters is the x piece. So if I have a constant in front of x, its integral is that constant times 1/2 x squared. I mean, the constant can't change that. Only my x can change what's going to happen to it, right? Yeah. Does that make sense?
Yes.
Because constants can just come out of the integral, so they don't matter.
Thank you.
Sure. What happened?
Oh, I think she needed to see something.
Oh, I'm sorry. Because you said it and then you didn't do anything. I'm like, why did I have to? You're just like, let me see if I can control him. Now move back. All right. All right, you guys. All right. So here's kind of that's section 5.4, like beaten to death. So just a little preview, and then we'll head out. Preview. What is the derivative of? You can do it, Jeff.
7.
What's this? Take a
1/2.
1/2
X squared minus 3 times 2.
times 2x.
To the negative 1.
1/2
Times 2x.
Yeah, better, let's see.
You can cancel 2.
X squared
It'll be
minus
x
3. Yeah.
Is that cool?
Yes.
I prefer chaos, to be honest. Managed chaos. Some of my classes, they don't say a damn thing. They scare me and they bore me.
So when you substitute x squared minus 3x.
Now watch. You ready? So if I want to integrate this, could I do it?
Use substitution, right?
I think, look what I wrote. Now I know some of you guys
Oh, you said 1.
know about USUB, some of us don't. So if you don't know about it, remember, any derivative I do, that's automatically an integration that I know. So I know the integration of this would be that, right? So what is this missing? The x piece. So this is, so we don't currently have a way. You can actually do this based off of some arc trig stuff. But based off of what we just did, I would have to have an x here, right? You guys kind of understand? So if there was an x there,
Can't you,
then the integral would be that plus c, right? All right, cool. So we're approaching this. I have to identify. So, for example, let me just try this out. So if I had this integral is the evil integral that is impossible to do by hand. But can you guys tell me what it's missing to be able to be done? More than 2x. A 2x, because the chain rule derivation would have a 2x show up, right? So one way we do this is, so if there was, if I let u equal x squared, what's du?
It's 2x.
2x. So in order for this to be done, this has to be in there. I can't find 2x dx. I can only find dx, so I can't integrate this. And this is actually this function is not elementary.
Is this one that
My dear ones.
comes into?
If you take 280, you can represent the answer to this with an infinite sum. Ooh, 280 is awesome. Yes?
Can't you just divide the 2x?
2x on the other side?
Of course you can't. I mean, tell me exactly how you would do it. I mean, what would happen?
Oh, well, but then we have a u and an x.
No.
Wouldn't you divide 2x?
I see. You guys have taken calc before.
No.
And I can hear already that your teacher taught you in a very not good way. So I'm going to try to correct that. And I will be completely blunt about this. Because there is a way to do u sub which is unbelievably stupid. Because it leaves the door open for you to make really simple mistakes. I'm not saying anything against you guys. But it sounds like maybe they taught. Did they teach you to do this kind of thing?
Yes.
Yeah. All right, that's crap. I know you might like it, and it works if you use it correctly. But it opens the door to so many stupid mistakes. Right? I don't know if you guys understand what I'm saying. Because you almost made a mistake. You can't do that. You can't divide by something. You can't. It's got to be in there. So a much better way. Now watch. The last thing in this, well, it's on the guy. So another way to do this. Now watch. Stay with me now. This is all, I can do this all day long. So in the same vein as you guys figured out what had to be here, what has to be here? A 3. So how could I legally put a 3 there as long as at the same time, so there's no way I can do this. Why not? Because that no x stuff can come out. You can't go out and no. See that. But constants, I can make the constant all day long. I can make it happen, right? As long as you got all the x stuff I need, and all I'm missing is a constant, I can make that happen all day long. They can come in and out, no problem.
So would you use the twister?
So what's the integral? So it'd be 1/3. The integral of this now is e to the 3x. That's a whole other way to get that 1/3. You don't have to just kind of come up with it because you realize it. You can come up with it because you put it there. There would have to be a 3 there, right? So you put a 1/3 at the same time. There's a whole other way to look at why there's an over 3 in that situation. So when we get deeper into U substitution, we'll see a lot more of these kind of things. All right. U sub is awesome. Oh yeah, so if you want to study group 36345A, the same one as last time. 345A.